All right, so I know that not everyone's in the room just yet, but just wanted to make a quick announcement that I have already finished evaluating Team 2's contribution, so I've already sent back my comments. I'm halfway through Team 3's contribution to manuscript, so I will give that back later today. I wanted to do this quick turnover because time-wise, there's not much left, and one of the major issues I'm seeing is that there's a really major lack of figures. And why that's a problem is because it's very hard for me to understand some of the material if I have no images to give me a visual of what you're talking about. So keep that in mind, because that's the same thing that will be a problem moving forward. You think about who's going to read this, there needs to be a visual representation of what you're talking about that helps provide the context that is necessary to establish many of the key points that you're trying to make. So figures are a must, whether you make them yourself or you find something in the literature that you are referencing. All right, so with that said, we're going to transition to today's seminar. I'm going to let Xiaomi, who's already presenting, to take over. So Xiaomi, I'll let you know as soon as you start the presentation part of your article when you have 2 minutes remaining.
Thank you. Adriana will be starting the presentation.
All right, great.
Can you guys hear me?
Yes.
Yes.
Okay, so good morning. My name is Adriana Vasquez, and together with my classmates, we will be presenting today's seminar about bio approaches for the use of metal-containing nanostructures. As discussed in class, many of the current drugs used to treat certain diseases lack specificity or can be degraded systemically before reaching the target, and this is a great threat for healthy cells and the overall health of the human system. That's why researchers are seeking alternatives for drug delivery that convey a high payload of a drug to specific sites in the body. These alternatives need to have characteristics that facilitate their bioapplicability to human systems and overall, ideally, reduce their impact to the environment. One of the recently researched alternatives for drug delivery systems is within the material science field, where nanostructure synthesis and application is a prominent subtopic. Particularly, nanoparticles are a feasible way to target the common problems in drug delivery, for example, the selectivity problem and the targeting. As we can see in the image, nanoparticles can be synthesized as different structures depending on the uses, the therapeutic uses that will be given, the materials used to synthesize them, or the methods used. We can have from nanodevices to nanopores to spherical silica porous components to nanoshells, nanotubes. It all depends on the application that will be given to them. Overall, nanomedicine, which contains the nanoparticle subtopic, is an emerging area of research. The potential scope of newly designed functional nanomaterials and their interactions at the cellular molecular level is broad, particularly for applications in the diagnosis, treatment, and prevention of complex diseases such as cancer, Parkinson's, etc. The biomedical approaches for the use of metal-containing nanostructures, which will be discussed in today's seminar, aim to evaluate a synthetic route for using S-glauca, which is a plant, for metal-based nanoparticles, zinc oxide metal nanoparticles, and their biocompatibility for future applications. I didn't broadly mention it in the introduction, but nanoparticle synthesis and common drug systems are synthesized, and some of them require a lot of solvents like THF, DMSO, which are detrimental for human health and environmental health also. The second aim of today's seminar is to evaluate the in vitro antimicrobial activity of the glutathione stabilized silver nanoparticles against several multi-drug resistant Campylobacter stains while studying the effects of these nanoparticles on different human intestinal cell lines. The third aim of the third paper is to reduce the side effects of platinum-based chemotherapeutic drugs and use green chemistry methods to synthesize platinum nanoparticles using T-polyphenol to ultimately evaluate the anti-cancer properties of said nanoparticles. Well, the first article we are going to discuss, my classmate Sayomi and I, is titled Bioactive and Biocompatible Nature of Green Synthesized Zinc Oxide Nanoparticles from Simaruba glauca, DC, an endemic plant to Western Ghats, India. As we already proposed in the previous introduction, nanoparticles are a feasible alternative to drug delivery systems. Although, as I said, it wasn't mentioned in depth, the techniques employed for the synthesis of nanoparticles have their drawbacks due to the use of toxic chemicals. As I said, some of the commonly used solvents like THF-DMSO are rather harmful because the synthesis, the industrial synthesis, be it from the pharmaceutical companies or the other alternatives, are rather harmful. The development of non-reliable, non-toxic, and eco-friendly methods for the synthesis of nanoparticles is being researched, and we wanted to include this couple of the many articles regarding green synthesis of nanoparticles we found. So you guys can actually see that this type of research is taking a lot of prominence presently and is in the front line. Particularly, this group of researchers were exploring a way to synthesize the zinc oxide nanoparticles because in recent years, plant extracts like aloe vera, for example, have been used and they have been effective. In this case, the nanoparticle they wanted to synthesize were the zinc oxide nanoparticles, which are reported to be practical due to their unique chemical and biological properties, including high surface area to volume ratio, which is essential if we want a greater active site, like to immobilize, be it enzymes, proteins, etc. The cytotoxicity dependent on concentration is also an essential property, because this can make way to individualized therapy. The dosing of many of the pharmaceuticals nowadays depend a lot on the individual. So to be able to tailor with the concentration and therefore the cytotoxicity effects is also an important parameter to be considered from these nanoparticles. And lastly, but one of the most important, it's the biocompatibility, because we don't want the zinc oxide nanoparticles to be harmful for the human health. The plant, the extract they wanted to use was from the Simaruba glauca, which is well known for its vast pharmacological properties, as they possess many bioactive compounds, which are involved in hemostatic properties, which is to stop bleeding, anthelmintic, antiparasitic, which are basically the same. They both target antiparasitic approaches. The antipyretic, which reduces fever, and the anticancerous, which is the one that is evaluated in this article with the antimitotic assays. Next, please. To summarize and be more concrete about the specific research aims, the first one was to synthesize and characterize the zinc oxide nanoparticles using the S. glauca plant extract. After the characterization, they assayed the antioxidant potential of the green synthesized zinc oxide nanoparticles, and further, the antimitotic and biocompatible nature of the zinc oxide nanoparticles. Lastly, they wanted to determine which was the overall effect of the zinc oxide nanoparticles on red blood cells. For this, the overall methodology they performed is going to be explained now. For the zinc oxide nanoparticle synthesis, they retrieved 50 grams of leaf material and extracted them with 100 milliliters of water. They filtrated and boiled the sample, to which they added 5 grams of zinc nitrate, which was the compound that helped to produce the zinc oxide nanoparticles. After this addition, they had like the product that was obtained from this was extracted and collected combusted at 300 degrees Celsius, and left in a furnace for 2 hours. The resulting product were the zinc oxide nanoparticles that were used throughout the study. Sayomi will further explain the characterization of the zinc oxide nanoparticles, but to give you an overview, the techniques that they employed to characterize the zinc oxide nanoparticles synthesized were UV spectroscopy, X-ray powder diffraction, the SEM electron microscopy, energy dispersive X-ray spectroscopy, and the FTIR to assay the functional groups and the connectivity in the nanoparticle produced. As I mentioned, they also evaluated the antioxidant potential of the synthesized nanoparticles by studying different radical scavenging methods and exposing the zinc oxide nanoparticles to these radical species. They used the PPH species, the peroxide, the superoxide, and the ABTS. As we didn't quite know which were the structures of DPPH and ABTS, we included them in the slide in the footing so you guys could see what was the structure of the used chemicals. The antimitotic nature of the zinc oxide nanoparticles was evaluated using an assay to characterize the genotoxicity of the nanoparticles. They used onion bulbs and they exposed them to different concentrations of zinc oxide nanoparticles for 24 hours. Why did they use the onion bulbs? It has been reported that they are a great model to model the cytotoxicity of compounds. They also submitted the onions to exposure with methotrexate and water, which were acting as controls. Though that is the structure of methotrexate, that is a commonly used anti-cancer agent, and water. After 24 hours of exposure with a solution of 6-2-3-2-1 alcohol, chloroform, and acetic acid, they stained the samples with 2% acetyl-oricin and 1 normality HCl. The stain tips were squashed using 45% acetic acid, and the mitotic index was calculated. For the biocompatibility of the zinc oxide nanoparticles, they performed a hemolytic assay on red blood cells. That figure 3 shows an overall scheme of the hemolytic assay, and it was recovered from previous literature. But to explain what they did exactly in this paper, they centrifuged 10 milliliters of blood from healthy volunteers. They washed the red blood cells with a phosphate buffer solution, and they resuspended them. 5% hematocrit resulted, and to those dilutions, they added different concentrations of zinc oxide nanoparticles. Those samples were incubated for 1 hour at 37 degrees Celsius and centrifuged, whereafter the free hemoglobin content was measured. And the formula here depicted is the one they used to calculate the hemolysis percentage. They lastly wanted to determine which was the direct effect of the zinc oxide nanoparticles on the red blood cell morphology. For this, they prepared samples for SEM microscopy. They used the red blood cells, which were treated with zinc oxide nanoparticles, and they centrifuged them and washed them with PBS. Those were the ones they categorized as treated red blood cells throughout the rest of the paper. Those were fixed with 5% formaldehyde for 3 hours, and they were then dehydrated. Once dehydrated, they were evaporated to dryness in a desiccator to be further examined in the SEM microscopy.
All right, now I'll be taking over and explaining the results of this research. Starting off with the green synthesis of zinc oxide nanoparticles from S. glauca. In this figure, we can see a possible mechanism for the formation of zinc oxide nanoparticles from aqueous S. glauca leaf extract, starting off with squalane, which is a triterpene and also a medicinally important bioactive compound. It was identified in this study in gas chromatography mass spectrometry and in Fourier transform infrared spectroscopy of S. glauca. We can also see the zinc nitrate right here on the right side. We observe the capping stage, in which squalane is able to occupy the zinc ions orbitals and produce the capping effect. Then this complex compound forms zinc oxide nanoparticles by calcination, which is also known as heat treating, and in this case at 300 degrees Celsius in a static air atmosphere, as my partner previously mentioned. Next, we have the ultraviolet visible spectral analysis of the nanoparticles. On the left side, we can see the UV absorption spectra, and if we look closer, we see an absorption peak at 367 nanometers. On the right side, we can see that the band gap energy difference has a value of 3.24 electron volts. Evidence shows that based on the absorption peak and band gap energy values, zinc oxide nanoparticles are considered as the main criteria for their beneficial aspects in pharmaceutical and biological fields. So that's a fun fact. Moving on to the X-ray powder diffraction spectra of the nanoparticles. The diffraction peaks obtained are narrow and they're stiff, and they show no prominent shifts. This lets us know that the synthesized zinc oxide nanoparticles are quite pure. These numbers on top in the parentheses are the planes of hexagonal quartzite for each peak, and quartzite is a crystal structure that has hexagonal symmetry. Here you can see an image of the hexagonal quartzite structure of zinc oxide nanoparticles, and this was obtained from a previous article. All right, now we have the scanning electron, microscopic, and energy dispersive spectroscopic analysis of the nanoparticles. Here on the left side, we can see a scanning electron microscopy image in which the synthesized nanoparticles appear to be aggregated, right? And then on the right side, we have the an energy dispersive spectrum, and this helps us confirm the purity of the synthesized nanoparticles, which in fact turned out to be 98.51% pure. All right, now we have the estimated crystallite size of the grain synthesized zinc oxide nanoparticles from S. glauca. In this table, we have different zinc oxide nanoparticle sizes that were measured, ranging from 17.12 all the way up to 37.15 nanometers. The average size of these nanoparticles was 25.3 nanometers, and these values are all below 100 nanometers. Therefore, they are not prone to phagocytic clearance by the reticuloendothelial system, and they're greater than 10 nanometers and thus are not readily secreted by the kidney. Moving on, we have the Fourier transform infrared spectroscopy analysis of aqueous leaf extract of S. glauca and its green synthesized zinc oxide nanoparticles. Starting off on the left side, we have the spectrum, which was obtained from the leaf extract with bands corresponding to an alcohol or phenol group at 3,272. Next, we have an aliphatic hydrocarbon group at 2,917.87, a primary amine group at 1,633.52, an aliphatic amine group at 1,034.17, and a triple bond at 616.78. All units of reciprocal centimeters. The spectrum also lacks a band at around 3,250 reciprocal centimeters, which lets us know that there was no moisture present in the sample. Next, on the right side, we can see that the spectrum obtained from the green synthesized nanoparticles. Here, there is a peak. Yes, there is a peak that is characteristic to metal nanoparticles, and it corresponds to a metal oxide bond. And this one specifically is at 528.04 reciprocal centimeters. Next, we have the antioxidant potential of green synthesized zinc oxide nanoparticles from S. glauca. By looking at this table, we can see that as the concentration of zinc oxide nanoparticles increased, so did the antioxidant potential. Therefore, we can say that there is a directly proportional relationship. I should also note that the values presented are actually the mean of 3 replicates. Moving on, we have the antimitotic potential of green synthesized zinc oxide nanoparticles from S. glauca. The mitotic index went from 43.06% at 100 micrograms per reciprocal milliliter of zinc oxide nanoparticles, all the way down to 17.46% at 500 micrograms per reciprocal milliliter of zinc oxide nanoparticles. Therefore, we can say that the greater the amount of zinc oxide nanoparticles, the greater the antimitotic activity. There is not a significant difference between the first 3 bars, and I should again note that the values mentioned are the mean of 3 replicates. Now we have the percentage of hemolysis measured by a spectrophotometer at 100 micrograms per reciprocal milliliter of zinc oxide nanoparticles. The hemolysis was 2.7%. At 500 micrograms per reciprocal milliliter of zinc oxide nanoparticles, the hemolysis was 6.4%, which goes over the 5% mark, and that is what's permitted in biomaterials. Therefore, the maximum amount of zinc oxide nanoparticles that can be utilized for hemolytic activity is 400 micrograms per reciprocal milliliter. Now we have the effect of green synthesized zinc oxide nanoparticles from S. glauca on red blood cells morphology. Here we have an image of erythrocytes that were exposed to green synthesized zinc oxide nanoparticles. The authors stated that there was no noticeable damage to the surface morphology. However, if we look at the red blood cells in the middle, we can see that they don't exactly have their signature crescent moon shape. Now, moving on to the concluding remarks. Green synthesized zinc oxide nanoparticles show promising evidence for their possible use as an anti-cancer treatment, and not only do they exhibit a high antioxidant potential, which is useful when dealing with hydroxyl radicals, they also presented a noticeable decrease in mitotic index, hinting at the possibility of functioning as antimitotic drugs, which can be used to treat cancer. And lastly, they are biocompatible with erythrocytes. As we know, red blood cells are the most common host cell in our bodies. However, they differ from other cells in the body, and they lack a nucleus in their structure. And after analyzing this paper, we would be interested in seeing other studies test the biocompatibility of the zinc oxide nanoparticles synthesized by using S. glauca in other cells in the body. Here are our references, and we want to thank you for your attention and your time, and welcome any questions.
All right, thank you. So if anyone has a question, feel free to get on your microphone or type your question in the chat room. All right, so I guess my first question to you guys is, what do you think is happening with regards to the extract of the S. glauca that's leading to then the formation of the zinc oxide after the combustion step? So what exactly is the extract facilitating?
Could you repeat the question one more time? I'm sorry.
All right, so my question has to do with this synthesis, proposed synthesis,
Yes.
where basically there's an extract from S. glauca, and then you're
Yes.
showing this squalene that appears to be involved. And so my question to you is, what exactly is this compound doing to try to enable the formation of these zinc oxide nanoparticles as facilitated by this combustion step?
Well, as you can see, the squalene sort of caps. This is called the capping step, and it basically surrounds the zinc ions. And then what really helps form these zinc oxide nanoparticles, that is what we mostly focus on in this study, is the calcination step, which is basically also known as heat treating, and they add a lot of heat. In this case, it was 300 degrees Celsius in a static air atmosphere, and that somehow forms the zinc oxide nanoparticles.
So in the absence of that compound, and if you, in theory, if you were to perform the same process, would zinc oxide nanoparticles not form?
In the absence of the calcination process, probably not. We would just have this complex structure right here that's...
Oh, no, in the absence of the squalene.
Oh, in the absence of the squalene? Well, we would need another material to help form. And in this case, we have squalene because it was retrieved from the S. glauca, and that's what makes it a green synthesized zinc oxide nanoparticle, which is...
I don't know if I'm adding to what Sayomi said, but as you can see, there is a sort of coordination between the double bonds of the squalenes with the zinc oxide nanopart with the zinc in the middle. So I really don't know, and the paper does not explain it specifically, but my guess would be that the zinc oxide nanoparticles could form with a system that facilitates the interaction between the double bonds and the zinc 2+. I don't know if that's
Right.
an educated guess.
Right. So from there, it looks like there's some sort of organometallic interaction going on, which it looks like it's like serving as a template to help control the formation of these nanoparticles, perhaps of a certain size. So you guys said that it's like an average of what, 25 nanometers. But I guess my curiosity has to go with what would happen without that compound, because I believe zinc oxide would form based on basically what's going on at a high temperature. So I guess my curiosity is somehow this enabling a certain size to form, because at the end of the day, at least from the data that you've presented, it doesn't look like anything from the actual extract or this compound is really sticking on to the zinc oxide. It's just that the zinc oxide has a certain size, and it seems to have a lattice indicative of a Wurtzite type structure. So I guess what we're mainly looking at is something that's serving as a template and not necessarily becoming part of the actual composition of this structure.
For sure, it's not like the zinc is not retaining anything from the squalene structure. So I would say it's like a stabilizing agent maybe that facilitates the synthesis.
Right, and perhaps a certain size. Yeah, because that zinc under those conditions would certainly form zinc oxide. Now, whether it's a nanoparticle form or some sort of amorphous form, that's something that I would have to look into. That was what my curiosity is, if you guys had more insight as to what exactly were they hoping for when they were using this extract, in terms of, what was their insight or what was their idea behind their approach. So, okay, so there's a question for you guys. So from Javier, do you know the difference between doing a SEM analysis to inorganic material versus cells?
The SEM analysis in inorganic compounds versus cells. That's what he asked, right?
Yeah.
Well, the paper does not specify it, but I do know that for example, SEM analysis, you have to have a coding that is conductive. So if you're going to code, and the authors don't mention it, but I think the red blood cells surely would have needed to be gold coated before. So I would say that the difference would be in the preparation. For example, they dehydrated the red blood cells in the process. So the water, the cytoplasm within the cells did not lyse or burst or change morphology when coated with gold. So to answer your question, I think in the preparation, you have to consider for cells that they do not burst, they do not break, they do not change conformation, versus, for example, inorganic compounds that you can just sputter coat them with gold or any other metal that's available for some the SEM microscopy. And yeah, I think that's pretty much it. Because, for example, if you want to do some analysis on transversal cuts of membranes, you have to use liquid nitrogen for it not to change the morphology of the already synthesized membrane. So I would guess that for the cells and the red blood cells and any other biological compound, it should be the same, like making sure it does retain the morphology. I don't know if that answers your question.
All right, thank you. My very last thing is, so I saw you presented information on measurements of band gap. Any insights to why they were doing these measurements?
No, they just presented the information, and it says the article did mention that the band gap size specifically of the zinc oxide nanoparticles makes it one of the nanoparticles that are considered as a main criteria for beneficial aspects. So I think they just showed this in order to confirm that this band gap size is what's been previously obtained in the literature, and just to like keep that going.
So it's like a characterization. Well, just to give you a little bit of context, zinc oxide nanoparticles, like titanium oxide, so these are semiconductors, right? And so you will often see in skin products, for instance, sunscreen, that they're included because of their property of absorbing UV. Mm-hmm. And so my question is more towards whether they were trying to synthesize this for potential applications. And so obviously this is a characteristic of measuring its band gap to understand whether it's retained a certain characteristic band gap as a semiconductor. So yeah, zinc oxides have this capacity to absorb UV. They're known to be some of the lesser toxic oxides. And so that's the context for you guys. All right, well, thank you very much. And so now we can switch over to the next set of presenters.
Yes.
All right, so good morning. My name is Rafael Delgado, and with my partner Javier Santiago, we will presenting the article Antibacterial Activity of glutathione stabilized silver nanoparticles against Campylobacter multi-drug resistant strains. So this is the article that we will be referring today. This article was developed in the Instituto de Investigación en Ciencias de la Alimentación in Madrid, Spain, by two groups. One of them is food microbiology and biocatalysis, and the other group was applied inological biotechnology. And it was published in 2018. In the introduction, Campylobacter is the leading cause of bacterial foodborne gastroenteritis worldwide, and more than 95% of the infections attributed to this genus are associated with the species Campylobacter jejuni, that is C. jejuni, and Campylobacter coli, that is C. coli. Patients may experience mild to severe illness, and symptoms can include gastrointestinal manifestations such as diarrhea, abdominal cramps, nausea, and fever. The severity of symptoms during the disease mainly depends on the infective strain and on the medical condition of the patient. On the other hand, there are potential severe long-term complications like many syndromes such as Guillain-Barré syndrome, Reiter's syndrome, or reactive arthritis. Antimicrobial resistance in bacteria from food of animal origin, including Campylobacter, has become in the last years a serious public health concern in both developed and developing nations. According to the paper, a rising amount of Campylobacter isolates have become resistant to different antibiotic families, and that's what we are going to see along the paper discussion. The increase in the incidence of infections caused by multi-drug resistant MDR, as we know, strains, let's say lower susceptibility to at least 3 antibiotic families of Campylobacter, makes the treatment of the disease increasingly complicated. In recent years, the use of silver nanoparticles as antibacterial agents has become more important specifically in the medical field due to the importance to provide alternatives to the resistance that many pathogenic microorganisms exhibit to most widely used antibiotics. Silver nanoparticles can be coated to facilitate their interaction with the environment, and that's the other thing important during this discussion. It's important to know that there are no previous studies about the impact of silver nanoparticles on Campylobacter, in spite of its importance as a foodborne pathogen. The cytotoxicity of nanoparticles is a major concern in the use and development of nanotechnology. The toxicity of nanoparticles to eukaryotic cells is associated to the higher reactivity of these particles due to the large surface. In vitro studies suggest that silver nanoparticles may induce cellular death, as we know, increase reactive oxygen species ROS production, oxidative stress, and DNA damage. The ROS is one of the most important things that will help this strategy to overcome drug resistance. The objective of this study, the main objective, was to evaluate the in vitro antimicrobial activity of GSH Ag glutathione silver nanoparticles against several strains of Campylobacter, as we discussed, also including the study of the effects of these nanoparticles on different human intestinal cell lines. With the materials and methods, we're going to briefly explain it. In the synthesis of glutathione stabilized silver nanoparticles, as GSAH AGNPs, as we abbreviate, silver tetrafluoroborate AgBF4 was firstly dissolved in water. The silver salt was reduced using sodium tetrahydroborate with vigorous stirring at room temperature. Then, after 30 minutes of stirring, 2 milliliters of glutathione solution in water was added dropwise to the silver colloidal solution. The obtained nanoparticles show a heterogeneous range of diameters between 10 and 50 nanometers. As we can see in that picture, the UVB's spectrum of water solution of GSH and Ps display an increased and sharp localized surface plasmon resonance band at 428 nanometers. These characteristics of the absorption band are due to the GSH complex in accordance to the size and dispersion of sizes obtained with the nanoparticles stabilized with glutathione. In the images on the top, in the A, we see the microscopic characterization of glutathione stabilized silvers nanoparticles at 100 nanometer, and in the B, we see the same thing but 50 nanometers. In this table, we can see the isolation source, species, strains designation, and isolation place of the strains that were used in this study. These strains were isolated from different sections of the chicken meat food chain and from cases diagnosed with Campylobacteriosis at Burgos University Hospital. As we can see the species that were C. jejuni and C. coli, and the isolation place, species, and isolation place of the patients, like pediatric unit, internal medicine unit, digestive unit, and others. The antibiotic susceptibility was assessed following a method based on the performance standards for antimicrobial susceptibility test described by the Clinical and Laboratory Standard Institute, and this was discussed in the article. Also, the evaluation procedure followed for the antibacterial activity of GSH, AGNPs, against C. jejuni 11168 was briefly explained in the paper too. According to the antibiotic susceptibility test, the antimicrobial disc plates were incubated for 48 hours. 9 antibiotics from the most frequently used against Campylobacter, representing 5 different families, and these were macrolides, quinolones, fluoroquinolones, tetracyclines, aminoglycosides, and beta-lactam antibiotics. Now, I let you with my partner, Javier.
Okay, now for the results and discussion. First, they hypothesized one mechanism of action. That is these silver nanoparticles release silver positive 1 molecules that react with sulfur and phosphorus at the surface of the bacterial cell. This leads to the production of ROS and eventually cell death. So the coating of glutathione on the surface of the silver nanoparticles provides the necessary solubility in aqueous environment in our body. The thiol groups shown in the glutathione attach to the silver nanoparticle surface, and the carboxylates and amines provide the water solubility. And these nanoparticles, as seen in the right picture, are between 10 and 50 nanometers. For the antibacterial activity of these silver nanoparticles against C. jejuni strain, they show that concentrations of 9.85 to 39.4 micrograms per milliliters were bactericidal to this C. jejuni strain after 24 hours. Bactericidal means that there's no more bacterial content left. These nanoparticles have proved to be more effective on gram-negative bacteria, possibly because of the thinner peptidoglycan layer they have in comparison with gram-positive. In the figure to the right, you can see the chart showing the last 3 concentrations that were bactericidal. And the antibiotic susceptibility test on the Campylobacter strains. All C. coli strains except C5 and C19, as shown before. These two were 2 of the clinical strains were susceptible to erythromycin, that is the first therapeutic option against severe Campylobacter infection. So that's a concern to take in consideration. 97.5% of the strains in this study were resistant to nalidixic acid, norfloxacin, ciprofloxacin, and tetracycline. There are some common antibiotics. A high level resistance, 67.5%, was found for ampicillin, and more moderate resistant, 32.5%, was found for amoxicillin. There are some other common antibiotics. Resistance to streptomycin in the study were relatively high, 35%, relatively higher than other studies compared to this one. And finally, only one strain was resistant to the antibiotic gentamicin. In the next slide, we can see all the studied antibiotics compared with the strains and the resistance above. All Campylobacter strains in the study are considered multi-drug resistant, MDR, since they show resistance to at least 3 different antimicrobial classes. So they then assess the antibacterial activity of these nanoparticles, several nanoparticles, against food chain and clinical Campylobacter strains. These silver nanoparticles were bactericidal for most of the strains, 87.5%, in a MBC range from 19.7 to 39.4 microgram per milliliter. MBC is the minimal bactericidal concentration. That is the concentration, minimal concentration for the bacteria to be eliminated completely. Food chain isolates show higher susceptibility to these silver nanoparticles than clinical isolates. And it's hypothesized that this is because clinical isolates are more strengthening than food chain isolates. %60% of food chain isolates presented MBC, that's the minimal bactericidal concentration, between 9.85 to 19.7 microgram per milliliter, and 100% of clinical isolates presented an MBC between 19.7 and 39.4 microgram per milliliter. Similar to the MBC, 80% of the food chain isolates presented an MIC, that is the minimal inhibited concentration, between 9.85 and 19.7 microgram per milliliter, and 80% of clinical isolates present an MIC between 19.7 and 39.4 microgram per milliliter. The MIC is the minimal concentration that for the bacterial to be inhibited, not completely extinguished. So then the authors reviewed the antibacterial mechanisms of the hypothesized mechanisms for these silver nanoparticles. Although the antibacterial mechanisms of nanoparticles are still unclear, they have hypothesized 4 pathways, at least, for these silver nanoparticles. One is they adhere to microbial cell surface, resulting in membrane damage and changes in transport activity. The second pathway is they penetrate inside the cell, affecting the cellular machinery. The third one, they modulate cellular signal system, causing cell death. And the fourth one, they cause increase in reactive oxygen species, ROS, inside the microbial cells, leading to cell damage. This fourth one is the hypothesize the better pathway that they think. The fact that the silver nanoparticles possess several bactericidal mechanisms may explain why bacteria resistant to them is rare and is effective for the bacteria antibiotics. Then the authors finally assess the effects of these silver nanoparticles in the viability of human intestinal cells to see the toxicity to normal cells. So they found exposure of these nanoparticles to epithelial cells showed a dose-dependent cytotoxic effect. So up to 4.93 microgram per milliliter showed no significant toxicity, but cell viability was impaired when observed greater concentrations of 9.85 microgram per milliliter. The MIC 50 value, that is the minimal inhibited concentration of 50% of all the bacteria for this nanoparticle is a value of 19.7 microgram milliliter, which means that the mean efficacy concentration of these nanoparticles against this Campylobacteria can be toxic to human epithelial cells. So other studies for the use of drug delivery system that aided in the protection the protected transportation of these silver nanoparticles will help the improvement of this antibacterial therapy. So in conclusion, the studied silver nanoparticles could have a potential applications to be used as antimicrobial agents and against Campylobacter. These nanoparticles have antimicrobial properties against MDR strains, but toxicity to human cells must be addressed. These silver nanoparticles could help to enhance antimicrobial strength of antibiotics or other bioactive compounds, contributing to reduced therapeutic doses and less cytotoxic effects and side effects. And finally, these silver nanoparticles will be potentially applicable in the different places of the food chain, like production of or processing of meats, or as an alternative to disinfectants.
Okay, so now with the perspective from Javier and me, the silver nanoparticles presented in this study provide a good alternative therapy for MDR bacteria. However, a good drug delivery system or encapsulating system must be applied to it in order to circumvent the toxicity issue to human intestinal cells. As the article said, in the last years, the antibiotics currently used are becoming less effective. We need more related research to improve technology with the benefits and potential of these strategies. These are the references. Any questions? Thank you for your attention.
All right, thank you. So if any classmates have questions, you can feel free, again, get on your microphone or ask a question. And Lisby was right away with one. Okay, so señalan una relación entre tamaño de nanoparticle y actividad.
La puedo contestar en español o en inglés. La voy a contestar en español.
Either one, remember.
En el artículo mencionan que que estudios pasados dicen como que mientras menor es el tamaño de la nanopartícula, pues mejor será la actividad antibacterial. Pero, como vimos en este artículo, hay veces o hay strains, hay tipos de bacterias que no necesariamente eso aplica, ya que en este artículo, como vimos, el tamaño de partículas comparado con artículos anteriores no es relativamente pequeño, es un poco más mayor y es más efectivo ante el Campylobacter. Así que usualmente mientras menor el tamaño de la partícula, pues mejor la actividad antibacterial, pero no necesariamente.
Okay, so you have another question, Daniela. Slide number 11. Why does the nanoparticles reaction with sulfur and phosphorus at the surface of the bacterial cell affect ROS production? Any ideas here?
I think Javier is more expert in that part than me.
I'm sorry, I'm reading the question now. Why do...
So, go ahead.
I don't know if the article mentions that nanoparticle reaction with sulfur and phosphorus affect the ROS production.
Well, so related to that question, so I have my own. So maybe we can think through this. So here in this slide, and I also mentioned it in my own discussion last lecture about how formation of silver plus can result in cytotoxic effects for the reasons you have listed there. My curiosity comes from this basically coating of the glutathione. So we know glutathione exists in both its oxidized and reduced form in the cellular environment. So in this context, supposedly the glutathione is helping to, you say there, to provide solubility, but I also wonder if it's facilitating some sort of redox activity of the silver itself. So I do wonder about in slide 17, when you talk about pathway forwards, what they think, do they think that this nanoparticle is somehow decomposing and then forming silver ions? Or is it that the interaction of the surface glutathione and the silver itself is basically forming something that is redox active, that, going to Daniela's question, could then be interacting with these other types of biomolecules with sulfur moieties, phosphorus moieties, or phosphate, whatever. So that's where my curiosity is as it relates to her question. Do you have any insight about that?
Okay, so in the paper they mentioned this coating, this glutathione coating, as a coat to make the nanoparticles more soluble in water.
Mm-hmm.
But they don't mention the glutathione molecules to be part of the ROS production. They mentioned that the nanoparticles that are in the zero state, they release silver +1 molecules, and those molecules are redox active, and those are the little molecules that produce the.
So do they do these abilities?
ROS.
So are the particles actually then decomposing?
That's one of the things that they said that we need to study more. But according to the paper and with what Javier said, they don't say nothing about ROS, but they said that the glutathione helps with the interaction with the environment. So that solubility with the intestinal cells and all that stuff, they said that we need more studies with regards with that.
Right. My question not necessarily was with Ross. It was more if it's forming some sort of redox active species, which does not necessarily have to form ROS. So I was just kind of wondering if that interaction of the surface with the glutathione with the basically this very reduced form of silver is somehow forming something that's redox active. So it's something that you guys can look up by looking up, redox potentials of silver, neutral silver glutathione complexes. That can give some insight into that. Okay, so I'm going to stop there. Glad somebody did have a question, so if you guys can answer it in the chat room. Let's move on to our next presenters.
Yeah, okay.
Can you see that?
Yes, I can see it.
Yes. So I will start. Good afternoon. Miguel and I, Gemily, will end today's seminar section with the article Brain Synthesis of Platinum Nanoparticles that induce cell death and G2M phase cell cycle arrest in human cervical cancer cells, published online in January 2015. The objective of the article can be summarized in 3 points. The first objective of the research is to increase the effectivity of the viability of drugs, reduce side effects, and prevent damage of other tissues. The second objective was to use green chemical methods to synthesize platinum nanoparticles using T-polyphenol as a reductant and surface modifying agent. The third objective was to assess the anti-cancer properties of the polyphenol functionality platinum particles prepared in human cervical cancer cells by assaying cell viability and analyzing nuclear morphological changes and distribution of the cell cycle using in vitro models. Cervical cancer is a type of cancer that occurred in cells of the cervix. Cervical cancer is a major risk in human health problems in developed countries, killing 270,000 women each day. According to the article, it is the second most common cancer worldwide and highly radio-resistant, and at least 370,000 new cases are identified each year. Here, there are different types of treatment depending on the stage of cancer. Here in the diagram, you can see them. And for advanced stage, it's used chemotherapy. So we were going to focus on that. So for many years, platinum-based chemotherapy drugs, including cisplatin, carboplatin, and oxaliplatin, have been used to manage cancer. Those drugs are not selective for cancer cells because normal cells are also affected, leading to substantial dose limit acute and chronic toxicity. Platinum is a metal and a member of the group 10 of the periodic table with the following electron configuration. The most important biological form are platinum 2 and 4 with electron configuration of D, A, square plane, and B6 octahedral. The health effects are associated with the type of bound ligand.
Okay. So T polyphenol, which we will call TPP, is a phytochemical extracted from tea leaves. The green chemistry methods for the synthesis of metal nanoparticles may offer a potential method to overcome the shortcomings of current synthetic routes. Natural phytochemicals are non-nutritive, biologically active chemical compounds that have antimicrobial, anti-inflammatory, anti-cancer, and antioxidant properties. Phytochemicals have induced apoptosis and cell cycle arrest in previous cell and animal studies, and the anti-cancer properties of phytochemicals were studied as a monotherapy or accompanied by chemotherapeutic drugs. T-polyphenol are effective free radical and singlet oxygen scavengers, possessing the potential to prevent a variety of diseases, including cardiovascular, hepatic, renal, neuropulmonary, and intestinal diseases, as well as cancer, diabetes, and arthritis. Recent studies have also demonstrated that a combination of T-polyphenol and cisplatin can synergistically induce apoptosis through both caspase-8 and caspase-9 activation in breast cancer cells and might not produce side effects. Platinum nanoparticles were fabricated using a green synthetic approach, mixing 5 milliliters of T-polyphenol with 25 milliliters of 0.001 molar chloroplatinic acid solution under magnetic stirring. After the color of the precursor solution changed, it was purified by centrifugation and washed twice with water.
The sample was analyzed in powder X-ray diffractometer of copper K alpha radiation. The change in the diffract X-ray intensity of pure phase were measured and analyzed with computer software to solve the structure of the sample. The XRD patterns of prepared samples show a peak at an angle of 39.4 with Miller index of 111, which correspond to phase center cubic platinum nanoparticle. The phase center cubic is defined with an atom on each corner and an atom on each face, with a total of 4 atoms per unit cell, a coordination number of 12, and an atom packaging factor of 74%. A transmission electron microscopy analyzing was done with a drop of the nanoparticle dispersed onto a carbon cotton copper grid and allowed to dry completely in a vacuum desiccator. The figures show and the team image of the nanoparticle, whose size varies between 30 to 16 nanometers, in the figure A with low magnitude and the figure B with high magnitude. The team image suggests a well-dispersed nanoparticle formation with the flower shape.
Okay, so the energy dispersive X-ray analysis called EDX, it showed that elemental profile of the prepared nanostructures with platinum, copper, and carbon. And the carbon and copper are presumed to come from the copper grid and the T-polyphenol, which demonstrates, and this also demonstrates that the particles were mostly reduced to nanoparticles of the rest are mostly associated with T-polyphenol. They characterized the nanoparticles here. These cervical cancer cells were plated in a density of of 1 times 10 to the 4 cells per well in 200 microliters of fresh culture medium. After they incubated overnight, these cells were treated with different concentrations of 25 to 200 micrograms over milliliters of the nanoparticles for 24 hours. And after the incubation, the 20 microliters of MTT solution was added to the well, and the plates were wrapped with aluminum foil and incubated at 37 degrees for 4 hours. The plates were centrifuged, and the purple formation product was dissolved by the addition of 100 microliters of DMSO to each well at a absorbance that was monitored at 570 nanometers. If we look at the figures, the results to interpret that the compound decreases the viability of the cells. It was shown that the nanoparticle was effective in a dose and time dependent manner, as we can see that at higher concentrations, the cell viability does decrease significantly. And the nuclear morphology of cells was examined using a PI staining under a fluorescence microscope. The fluorescence microscopic images of the nanoparticles in treated and untreated cells is shown in the figure. To make it a little bit more clear, I will explain kind of what it is. The first column is kind of the control groups. This would be the control group after 24 hours, and this would be the control group after 48 hours. And it would be the same logic, but in this case, the nanoparticle would be at its IC50, and here would be at its IC75, both at 24 hours and 48 hours. The results do show that the nuclear morphological changes via apoptosis, and when compared to the controls, the treated cells did show a higher percentage of cells with abnormal nuclear patterns following treatment with increasing concentrations of the nanoparticles. The data collected from the manual counting of cells with normal and abnormal features are shown in that the number of apoptotic cells increase in both a time and dose-dependent manner. The cell cycle analysis, well, the researchers evaluated the effect of the nanoparticles on the cell cycle of human cervical cancer cells by flow cytometry. The cells were exposed to different concentrations of the nanoparticles. Like I mentioned before, it would be the same concentration in the IC50. It would be 18.34 micrograms over milliliters, and the IC75 would be 11.4 micrograms over milliliters. Then the results were done after 24 hours. Some of the results we could see is that with increasing concentration, the proportion of GO and of cells in the G0 and the G1 does decrease, suggesting that there is more growth in the G1, and the S phase also significantly decreases. And this is also accompanied by a proportion in the cells of the G2 and mitosis phase, and the G2 does increase in comparison. The nanoparticles did induce a dose-dependent cell phase distribution in the cells, which indicates the proportion of G2 to M phase cell cycle arrest due to DNA damage.
So with this, we can conclude that the biosynthesis of the nanoparticle using polyphenol is a cheap, simple, and eco-friendly process. And fun fact today is the Earth Day. It's Earth Day, so that is nice to be like talking about an article that talk about a green synthesis. The synthesis of the nanoparticle will characterized by various techniques using UVVs, spectroscopy, TEM, XRD, and EDX. The team image show well dispersed to 30 to 60 nanometers size, the nanoparticle with a flower shape. The nanoparticle have cytotoxicity properties that inhibit cell proliferation and induce apoptosis in human cervical cancer cells. In the cell cycle phase distribution, nanoparticle trigger that due to over-end phase cell cycle arrest. Those findings emphasize that the nanoparticle have potential anti-cancer properties and have the ability as cancer therapists. Therefore, this article presentation had excellent and anti-cancer property for the use of metals containing nanostructure. Thank you for your attention. Any question?
All right, thank you. So again, if any classmates have questions, please post your questions, or you can also get into your microphone to ask. All right, so I do have questions. I guess I would like some insight as to what you guys think is the mechanism of action of these platinum nanoparticles, especially with the incorporation of the TPP component. What do you guys think is going on here?
¿Podría responder en español?
You guys know that you can, so please feel free.
Ok, pues, ok, yo sé que es el mecanismo de cisplatin es un mecanismo que ya lo habíamos discutido en clase, que es el passive diffusion. Y pues hablando acerca de eso, como que el tamaño de esa droga es como que 5 nanómetros, pero entonces como que estoy haciendo una asociación porque hay estudios que dicen que tienen como que el mismo efecto, y pues se hizo un estudio con cisplatin y los tipolifenol. Entonces, pues yo opino que podría ser un mecanismo bastante parecido, dañando como que el DNA, pero no estoy muy segura si podría entrar como que esa nanopartícula por la superficie de la célula, como passive diffusion, perdón.
Okay, so that's speaking about the what you think may be happening as far as the platinum. What exactly is the TPP facilitating?
Pues yo lo veo más bien como si fuese facilitando la entrada hacia las células, porque para crear como que rodear el metal y que pueda entrar, como que pueda pasar por la célula. No sé si me explico bien. Es como ejemplo, si fuese un lípido que está rodeando un metal, y como el lípido es bastante parecido a la membrana, pues permite la entrada hacia la célula.
Un lípido en qué sentido? De que the backbone is like a lipid, because certainly not the actual catechol component. Yeah, I'm not sure about that answer, but I guess I'm not sure what exactly, like, is the nanoparticle, I guess it's a similar question as I had for the previous group. Is the nanoparticle believed to be falling apart so that the platinum is actually potentially reaching DNA, as Gemily was suggesting? Were there like any, yeah, I figured that that's something what they were going for, but it's not very clear to me.
Yeah.
What they were trying to do with it. Go ahead.
Exacto. Yo lo que pienso más bien es que es para poder facilitar la entrada hacia hacia la célula para que ocurra el DNA damage. Pero pues sí tengo dudas y eso queda como que ellos dijeron que lo iban a estudiar el mecanismo de la nanopartícula.
Y el platino, is it actually, is the platinum neutral? Is it charged? Because I'm not sure.
Para mí está cargado porque ellos usan chloroplatinum acid. Y para mí, yo pienso que puede ser que tenga una carga de manto.
De manto. So, hablando de eso, que yo veo que Maris te pregunta algo de the lattice, pero I guess my question here is, so if it's platinum 2+, right? What's providing the charge balance to the nanoparticles?
Pues, yo opino, puedes ir a las estructuras de los TS. De alguna forma, en uno de los artículos salen que los que están a la derecha son los que le están brindando esa estabilidad a la nanopartícula.
So I can imagine that those catechol type moieties, maybe even some of the carboxylates are coordinating onto the metal. My question had to do with the nanoparticle part. You know, whenever you have any small molecule or material, it needs to be charge balanced. So it's not, it can't just be that they're just platinum ions interacting with one another, but nothing that's actually providing for the stability. So yeah, you guys have to think a little bit more about what's the structure here. Because clearly, yes, I see that the platinum, they're basically interacting with one another, but think about the charge here. Okay, so I think that should be enough for now. All right, everyone, so thank you so much for your presentations. I will get Team 3 your feedback later today for your article. All right, I'll see you guys next week. Take care.